When it asks us to find the possible rational roots of each equation, it's not asking us to actually figure out which ones work. It's just asking us for a list of the possibilities. So what I want to do here is I want to list out the factors of p. Remember that p is the last number or the constant number. It has to be a number with no x. And the factors is just saying what are all the numbers that you could divide out of that number. So 1 and 3 are the only numbers you could divide out of the number 3. I put a plus or minus in front of each one because it could be a positive or a negative of that number. I don't actually care what the sign is right here because I'm going to put a plus minus in front of every single number. Now I need to figure out the factors of Q. The factors of Q, Q first of all is just the number 1. You can't see it there, but it's the number that's in front of your first term. The factors of 1 it's just 1. So now what I'm going to do is I'm going to make a fraction for p over q, and I'm going to put all of my factors of p on the top, and then all of my q factors on the bottom. And now what I'm going to do is I'm going to make a list because I don't want to leave my answer as this big weird fraction. I want to write out all the possibilities. So what I like to do is take everything that's on the top of the fraction and I like to divide it by the number on the bottom. So what I'm doing here is I'm going to do 1 divided by 1, which is 1, and the plus or minus just kind of hangs along with everything. And then I'm going to do 3 divided by 1, which is 3. So here are my options. There are actually total 4 possibilities here because I have positive 1, negative 1, positive 3, and negative 3. It looks like 2, but each of those has a positive and a negative, so it's actually 4. All right, for example number 2, my p numbers are going to be factors of 8. The numbers that divide into 8 are 1, 2, 4, and 8. And then I need, for my q numbers, I need factors of 2. So that would be positive and negative 1, positive and negative 2. So now I'm going to do the same thing with my p and q. Factors of p go in the numerator. And then factors of q go in the denominator. This one's going to be slightly more complicated because I have 2 numbers in the denominator. So what I like to do is go through, I'm going to take all the purple numbers and divide everything by 1. Now that's not going to change any of my numbers, so I'm going to have plus or minus 1, 2, 4, and 8. And now I'm going to do the same thing, but I'm going to take all the purple numbers and now divide them by 2. So I have 1 divided by 2, 2 divided by 2, 4 divided by 2, and 8 divided by 2. Now one thing that's a little bit tricky, if I take 2 and I divide it by 2, so I'm looking at this one right here, 2 divided by 2 equals 1. I already have 1 in my list. So this one is a repeat and I don't need to write it again. 4 divided by 2 is 2, which I already have in my list, so another repeat. And then 8 divided by 2 is also 4, which is part of my list already. So my final answer is only the part of the list that doesn't repeat itself. So just those 5 answers. It's actually 10 answers though, because you have a positive and negative for each. This example is the exact same example as the first example. So rather than figuring out what all the p and q numbers would be, I'm just going to copy them down. So this is just coming from that first example again. So we decided that the possible rational roots for p over q were plus or minus 1 and plus or minus 3. And this is from previous example. So now what we're going to have to do, and this is doing things the long way, is we are going to use one of those 3 methods. And I'm actually going to do this one by synthetic division, and then I'm going to do the next 2 by plugging in. Because I want to show you a shortcut on the calculator for those. So I have 4 possibilities. I have positive 1, negative 1, +3, and -3. So in order to use synthetic division, I'm going to take these 4 numbers as my possibilities, and those become the numbers that are outside of my synthetic division. I'm going to do this same exact thing 4 times with different numbers. So now I have to get the coefficients from my original problem. So I would have 1, 1, -3, -3. So 1, 1, -3, -3. And this is going to be the same for all of them, but I'll do that later. So now I'm going to go through and actually do the synthetic division. So I'm going to bring down 1. Remember, I'm multiplying this number by these bottom numbers here. So 1 times 1 is 1. And then I'm adding down to get 2. Now I multiply this 1 again times 2 to get 2. Add down, I get -1. And then 1 times -1 is -1. And if you add down, you get -4. So since I did not get 0 for my remainder, it means that +1 is not one of my roots. Now I'm going to repeat this process 3 more times. So remember, I'm using the exact same numbers, 1, 1, -3, -3. So bring down the 1. -1 times 1 is -1. This gives me 0. -1 times 0 is 0. Add down, multiply. -3 plus 3 is 0. So this one did give me 0. What that means is that -1 is a rational root of this problem. But now I have to keep checking because the other 2 could possibly work. So I have 1, 1, -3, -3. Bring down the 1. This would be 3, 4, 12, 9, 27, and 24. So this one is not 0. That means 3 is not a rational root. And then last one, so I'm going to bring down the 1, -3, -2, 6, 3, -9, -12. So again, not 0. That means that the only rational root from this problem is -1. So this is, again, the long way of doing this. I'm going to show you in a couple slides how you are going to do. You can use your calculator to save yourself quite a bit of time. But this is how you would actually do it without a graphing calculator.
I'm going to use Desmos to plug in my possible rational roots into the function to see which ones are actually rational roots. I'm in the graphing calculator for Desmos. The first thing that I want to do is show you what is actually happening. So what we're doing with each of these rational roots is we're plugging them in everywhere we see an x. So the first thing I want to do, I'm going to start with our first possibility, which you can see on the left, which is +1. And everywhere there's an x in my original function, I'm going to replace it with a 1 in parentheses. So I'm going to do 1 cubed minus 7 times 1 minus 6. So I took all of my x's and I replaced it with one of my possible rational roots, which is 1. And it tells me that my answer is -12. And so that's why you see on the left side there, it says 1, and then there's an arrow pointing to -12. If you plug in x equals 1, the answer or the value of that function at 1 is -12. But I want to show you a way that you can actually do this a little bit quicker. So the first thing we have to do is type in the function exactly how you see it typed on this slide. So I'm going to type in x cubed minus 7x minus 6, and you can see that in black it has graphed the function, so you can see that that's a cubic function. And then I'm going to press enter to go down to my next thing here. So now all I'm going to have to do is put in place, instead of f of x, I want to really find f of 1. So I'm going to type in f of 1, and you can see that it takes me straight to this answer without me having to type out the whole thing. So here's f of 1, which is -12. We already talked about where that comes from. And now I'm just going to replace this 1 with all of our different rational roots. So now I'm going to replace it with 2. That also gives me -12, and you can see that on the left, f of 2 is -12. Now I'm going to replace that 2 with a 3, and that one gives me 0. So that's why I have a pink box around 3 as one of my rational roots, because whenever you plug in a possible rational root and it gives you a value of 0, that is a rational root. And you can actually see it on the graph over here. If I click over here, you can see that this is the 0.30. And remember that rational roots means where rational numbers where the graph crosses the x-axis. So This crosses the x-axis right here at x equals 3. That's why I got this 0. Okay, now I'm going to continue on. So I did f of 6. That gives me 168. So that is not a rational root. And you can see that 168 on the left side of my slide. Now I'm going to put in -1. That gives me another 0. And again, you can see it on the graph here. So -1, 0. That's why that is giving me a 0, is because it is an x-intercept. -2 also gives me a 0. Here's where it is on the graph. So you can actually really see all 3 of these zeros on the graph. And then if I plugged in -3, that gives me -12. And finally, -6 gives me -180. And just something to keep in mind, because this is a cubic function, since I know that the highest exponent is the maximum number of rational roots, or roots in general, that I can have. Since I got 3 rational roots, I knew that -3 and -6 wouldn't work because I couldn't have more than 3.
We're going to use the same method to test all of our rational roots as we did in the previous example. The first step is to type in the function exactly how it's written in the notes. It is very important that you type it in exactly how you see it. If you make any mistakes, it's going to give you wrong answers when we evaluate. So here's my function, and one thing that I want to point out is that before even testing any of these in the calculator, you can actually see the answers. Remember that the rational roots are rational numbers, rational x values, where the graph crosses the x-axis. So I can see that it crosses the x-axis here at 4, 0, here at 2, 0, and then again at -0.5 or -1/2, 0. So I can already see that those are going to be my 3 x values that will give me zeros. And you can see that on the left side of the screen. Those are the 3 rational roots that I have put a box around, because those are my rational roots. But again, I want to show you how you evaluate this. So I'm clicking down here to bring up a new box, and I have to type in f of, and then I individually have to go through and test each of these rational roots. So if I put in f of 1, it gives me a value of 9, and I want to show you what that means on this graph. What that means is that if I go to my x value of 1, that on the graph, you can see that it's the 0.19. So all this is doing is it's evaluating the function at each x value. Basically, it's giving you an ordered pair. It's telling you if my x value is 1, my y value is 9, and that would be an ordered pair on your graph. But the bottom line is that what we're actually looking for are zeros. And so since this 9 is not a 0, that is not an answer. So I'm going to erase the 1 and put in the 2. That gives me one of my zeros. Not unexpected. We already talked about how you can see it on the graph. If you plugged in 4, also a 0, and we already talked about that as well. If I plugged in 8, it gives me 408. So what that's telling me is that if I followed this graph, where my x value is 8, if I went all the way up to the graph, it would be the ordered pair 8, 408 on this graph. I'm not going to do that because that would require quite a bit of zooming out, but that's what it would mean. Here we have 1/2, x equals 1/2. That means my y value is 10.5, but that's not 0, so that's not what I'm looking for. If I plug in -1, I get -15, so also not a rational root. If I type in -2, it gives me -72, not a rational root. -4 gives me -336, not a rational root. There's -8, that's a huge number for my y value, not a rational root. And then finally, -1/2, which we know is our final answer. So there are 3 rational roots of this function. We were able to see all 3 of them on our graph before we tested them. But if you needed to test them without being able to see a graph, this is what you would need to do. For our next example, I'm going to show you a different way to use Desmos to evaluate your possible rational roots. And I happen to think this way is a little bit more efficient. So instead of typing in our function into the first line here, we're going to go to this plus sign where it says add item, and we're going to select table. Up at the top of the table, I'm going to change a couple things. I'm going to change this where it says x1. I'm just going to change it to x. And then instead of y1, I'm going to change it to just the right side of my equation. So that would be 5x cubed plus 62x squared plus 59x plus 14. So again, it is very important that you type in your function exactly how you see it typed on the problem. Okay, so now the next thing is we're going to add values into the X column of our table, and the values we're going to add in are all of our possible rational roots. So I'm going to type in 1, -1, 2, -2, 7, -7. So you can see all I'm doing is I'm taking all of these numbers that were in my list and I'm just making one big table. 1/5, -1/5, 2/5, -2/5, 7/5. So it's still a little bit tedious to type all these things out, but then at the end I'll show you how it's actually going to give us our answers quite easily. So all we need to do now is look at our table, and anything that has a 0 in your Y column is one of our rational roots. So I can see that if I look at my whole table, I only have one value that came out to be 0. So that tells me that I have a rational root at this X value. So it's actually the calculator is doing the same process. It's taking all of these numbers and it's plugging them into the function, and then it's telling us what the Y value would be. So these are actually all ordered pairs that you would find on the graph. But the ones that we really care about, our answers, our rational roots, are the only ones that give us 0 as a Y value. So in this problem, our answer is -2/5. You can also see that I wrote it as 0.4. It just depends on your preference, but those numbers are actually the same, so it doesn't really matter. We're going to do the same process for this example. We're going to go up to the plus sign to add an item, and we're going to add a table. I'm going to replace x1 with just plain x. And then I'm going to replace y1 with my function, exactly how you see it in your notes. 6x cubed plus 12x squared minus 3x plus 8. So again, I can't say how important it is that you make sure that you type in your problem exactly how you see it. Otherwise, you will not get the right answers. Now, this is the part that's kind of a pain. We just have to go through and type in all of our possibilities. And in this problem, we have even more possibilities than we did in the previous. So I'm going to do 1, -1, 2, -2, 4, -4, and the numbers don't really matter. I said that wrong. The order of the numbers doesn't matter. So I just happen to go through and I'm doing the positive and negative of each number, but you could go through and do all the positives and then go through and do all the negatives. Either way, as long as you're testing all of the numbers, the order of those numbers doesn't matter. So I'm just typing in all these numbers, positive and negative. All right, last one, 8/6 and -8/6. Okay, so I've got all of my possibilities here. And again, I'm looking at just my Y values. Anything that has a Y value of 0 is one of my rational roots. So what you'll notice here is that I typed in every single one of the possibilities and none of them says 0. So what that tells me is that this graph doesn't have any rational roots. For our last example, it's going to be a lot easier for us to type this into our calculator. We don't have quite as many possibilities, but there is something different that happens that I want to make sure we talk about. So I'm going to type in, replace x1 with x. I'm going to replace y1 with the function, the right side of the equation. So 2x cubed minus 3x squared plus 1. All right, and now when I put in my possibilities, I only have 4 of them. I have 1, -1, 1/2, and -1/2. All right, so here's my list. It's a very short list this time, and I can see that I have 2 zeros. So I have a 0 at 1 and a 0 at -1/2. So that tells me that those are both my rational roots. There's something that I think will make a little bit more sense when we do the next lesson, when we're finding all of the rational roots, but I can tell you based on this equation that this equation, this function has 3 zeros. It has 3 roots. And I can tell you that 2 of them are showing up on my table. But the catch is that anytime you have an irrational root, so that would be something that you'd have to use the quadratic formula for, where you get something with a radical, or something with an I in it, something imaginary. Those numbers always have to come in pairs. And that's because when you use the quadratic formula, you have a plus minus situation, so that it's always going to provide you two answers. So since I have 2 of my 3 answers, I don't have room to have a pair of anything else. So what that tells me is that one of these zeros is a double zero. And I want to show you, I'm going to actually graph this so you can see what it looks like. So I'm going to put in f of x, and then I'm going to type in the same thing, the same function, 2x cubed minus 3x squared plus 1. And if you remember when we talked at the very beginning of this unit, we talked about how if you have a 0 that bounces off the x-axis, so here it's bouncing off and going back up, those are considered double zeros. And what that means is that that root, or that 0, actually happens twice. And again, I think this is going to come together for you when you see what that looks like when we divide out and find all the zeros in the last lesson of the unit. But I just wanted to point out that anytime that you don't have room to have a pair of extra roots, that means that at least one of your rational roots is a double zero. And a good way to figure out which one is the double zero is to graph it. So I can tell you that I know that I have 2 rational zeros, -1/2 and 1, but by looking at the graph, I can tell you that 1 is the double zero.